Hey, what's up, man? How are you? Let me do a quick run through of how the convolution works. So suppose you have this image, a 6x6 image in a grayscale. So each one of these blocks are the pixels and they range from 0 to 255, okay? Depending on what you want to do, like the application of the kernel is actually very straightforward. And I'll try to explain this as easy as possible, but I'm positive you're gonna understand, dude. It's very straightforward. So this is your image, okay? Now let's move it over here. Let's say you want to perform a 3x3 convolution. So for that you need a window. It's they call it convolution kernel. You might have heard of it already. And you can choose whatever you want to go in these blocks. Anything you want, absolutely anything you want. But depending on what you choose, you're gonna get something out. So basically you're gonna take this and you're gonna apply to this image, okay? Now let me show you what's gonna happen. Suppose let's say we pick something easy. Let me organize this real quick so I can write. Let's say here we pick 0, here we pick 1, here we pick 0, here we pick 1, 0, 1, 0, 1, 0. The reason I'm picking these values is just so that the calculation is much faster. In fact, I might not even make the calculation by hand because the numbers that I have here are not that simple. Okay? Alright. Oh, focus. Alright, let's do it. Dude, the application is very straightforward. What's gonna happen is the following. We're gonna take this square and we're gonna basically slide through the image. So this first, the square is gonna first come over here. So basically what you're gonna have is, for the first, you're gonna have this. 0 multiplies 111 plus 1 multiplies 222 plus 0 times 163 and so on and so forth. This row will multiply this row and still sum. You're summing everything. And finally this row is going to multiply this row. For the sake of the calculation, let's just do this one. So it's basically, these are all going to be zeros, so all we need to do is add these 4 squares, okay? So it's 222 plus 225 plus 92 plus 110. And no, I cannot do this by head, so let's go just do this. 222, 32, no, not 32, pardon me. It's 222, 225, 110 and 92. Okay, so this is gonna be 7, 9, 13, 14, 6. So you're gonna take this value, and once you apply to this image, the new image is gonna look like this. It's gonna be just 4 square. 1 second, let me just take out one real quick. I forgot about this portion of the example. So it's gonna be 4 okay. Alright. So we took this, we multiplied this, and we got this number, 649. So the value for the first here is going to be 649. Okay? Now we slide this. It started here. We slide it by 1. So now the square that we're looking at, like the multiplication, is going to be here. So we're now convolving this portion of the image with this 3x3 multiplication scheme. So now you're summing 163, 32, 215, 184. and it's gonna give you a number. Let's say for like, just add these numbers. It's gonna give you some number. I'm not gonna do it, but it's gonna be, I don't know, 514. Okay? Take this, slide once more. Now you have this, and then this, and then you slide one down. Now you're looking at this. Oh, here, here, and then you do the same thing. So the block basically slides through the image, and you only get the center of it. So basically everything you convolve becomes the center of another image. So we started with a 6x6 image, and because it's a 3x3 convolution, it drops to a 4x4 as an output. So your image decreases as you do this. If you made a bigger one, if you made a 5x5, if this was a 5x5 convolution, then you'd basically do 1, 2, 3, 4, 5. So it'd basically be this huge square here, and then you do some combination that you choose to multiply. And it's gonna, so basically you'd have a 2x2 image, because you'd be able to slide the kernel 1, and then 2, and then 3, and finally 4. So a 5x5 kernel operation would reduce the 6x6 image to a 2x2. So basically the output would be 4 pixels with some value, some value, some value, some value, depending on what you have there. I hope this helps, man.